So hey everyone, morning. I will be speaking about essentially, building algorithms that can automatically prove peephole rewrites for arbitrary width. I'm going to start out by motivating why this is even a sensible thing to do, and then explaining some of the algorithms that we use. So feel invited to ask a question as I'm speaking, and I hope we all have fun. Right. So let's begin. First, I'd like to thank a bunch of people that I work with, not sort of by naming all of them individually, because it's a lot of people, but essentially we work on this in the context of a proof assistant called Lean. A lot of the development is driven by a research organization called as the Lean Focused Research Organization. So we collaborate with them, and I'd like to thank sort of the people who run all of this, and the person who maintains a lot of the fixed width solver in Lean is Henrik Boving. So yeah, great. Okay. Yes, so first of all, we all know that Alive is awesome. For people who haven't seen what Alive is, here's a quick 1-minute intro. So let's suppose you want to show that these two programs are equivalent, which is to say that when your integers are 32-bit, dividing by 8192 produces the same value as shifting right by 13. So essentially what you can do is to write this source and target program and to ask this tool called Alive, hey Alive, are the two programs the same? As in, do the programs produce the same output for the same inputs? And Alive basically says transformation seems to be correct, because it is true that these two programs always give the same output for the same input. The seams is interesting, but yeah, we'll come back to that later. But you can generally trust Alive. Right, so now if I change the program and I change the division to be division by 1, Alive then says, hey, this transformation doesn't verify, and here's a precise counter example that I can give you, wherein when the source program produces the output 1 for the input 1, and the target program produces the output 0. So this rewrite is not sound, right? This is like not a correct rewrite. This is great. And if we sort of look at the LLVM code base, commits to InstCombine, which is LLVM's peephole rewriter, very commonly just reference Alive, right? Because this just means that you don't need to argue about whether a rewrite is correct or not. Alive has told you that the rewrite is correct. And I just point out examples of people using Alive to witness the fact that a lot of their rewrites are correct. Anyway, you can find tons. So then the question is, okay, this is great, but how does it actually work, right? It seems like magic. So roughly speaking, what it does is it takes your problem and it converts it to a different dialect, shall we say. This is a logical language called SMT-lib. And in particular, the first line that says set_logic QF UFBV is some kind of theory, right? Which is to say you're using the quantifier-free theory of uninterpreted functions and bitvectors, whatever that means. And you define the meaning of the source and target program, and you then ask a genie, which in this case is an SMT solver. Hey, does the source and target equal? Do the two functions called source and target produce the same output for all inputs? And I cannot go into detail on how precisely these works. There are a bunch of papers by Nuno et al. These are really great papers if you want to precisely understand how this works. But in broad strokes, this is the idea. And then the solver is a genie. It tells you whether it works or not. Okay, but so we take LLVM, it converts it into its own encoding, and then it asks the solver, right? This is how it works. So now there's an interesting question, right? Do you really trust an SMT solver? So to most people in the audience, the answer is yes. But an SMT solver is a large amount of C++ code, right? And SMT solvers also have bugs. It's not immune from magic, right? So for example, Bitwidth's law, it's an SMT solver for this bitvector theory and this uninterpreted function theory. It is in fact the best solver currently on the planet as of 2024. They won the competitions basically, and they also have errors, right? People make bugs. This is maybe not catastrophic, but it would be nice to not have to worry about whether your solver is correct or not. So that's sort of one source of error that we're interested in eliminating, right? We want sort of a fully verified system. But the interesting thing is, if you're writing a solver, the solver can't actually know what bit width you're going to give it as input. The solver internally needs to prove things for any given bit width, because when you feed it 32 or 64 or 128, its algorithms need to work, right? So somehow the internals of a solver need to be proven correct for arbitrary bit width, even though the solver only works for fixed bit width. And then the other thing so for like a really quick exposition of why this is the case. So here's sort of how the fixed width solver works. It takes a bit vector formula, it converts it into a SAT problem, and then the SAT solver like tells you that it's correct, and you can check the certificate from a SAT solver. I'm going to skip over how we check the certificate of the SAT solver. If you're interested, you can come and talk to me. It's called RAT. So this part is done. The part where we query the SAT solver is done, but the reduction from the bit vector problem to the SAT problem is complicated. So for example, suppose you think of addition, right? So addition is a thing you can do on bit vectors. But if you sort of think about how we define the meaning of addition, we say take the bits, convert it to natural numbers, and then produce the output, right? Like give the output this way. But you can't convert this natural number problem into a SAT solver problem. So instead, what you're forced to do is you're forced to build a Boolean circuit, which we learn in, I don't know, uni, I guess, of how to, add numbers, right? So this lets you convert it to a SAT problem. But, this particular circuit I showed you, it's only for 3 bits. But sort of this translation needs to happen for any bit width. So even though the solver, when you instantiate it, is solving the 3-bit problem, if you're trying to prove the solver itself correct, you need to prove that this is correct for an arbitrary bit width, because you can invoke the solver for an arbitrary bit width. So that's sort of, like one place as to why we would like these sort of arbitrary width solvers. The other thing is that, people have started to use pretty gigantic bit vectors. Like SV has these 2048 wide vectors, and fully homomorphic encryption compilers also use like really wide registers to store their polynomials. So I would sleep better at night knowing that these rewrites we do are actually proven correct for arbitrary width. So this also, once again, tells us what, just prove the theorems for arbitrary width. Don't fix your bit width to be 32 or 64 or whatever. Just actually try to prove it for all bit width. Yes, I know this is undecidable, but as I heard somebody say today, most interesting problems are, right? So we're going to pick subsets of the problems that are actually solvable. So now, okay, I'm going to go into the algorithmic side of things as to how these work. I'm going to present 2 algorithms, one that's based on a view in terms of automata theory to prove these theorems for arbitrary bit width, and one that's somehow based on analyzing the structure for 1 bit and then generalizing it to n bit. Great, so let's basically jump into one of these algorithms that is based on automata theory. So we're trying to prove that the bitwise AND operation is idempotent, right? So we're trying to say that for all bit widths, importantly, for all bit vectors of that width, if you take x and x, you get x. So we know this is true. And yeah, so sort of how do we know this is true? Well, the idea is, okay, let's consider, like bit streams of these inputs x. So, the first bit is x0 and x0, and when we take the bitwise AND, we get x0 and x0. And then we can evaluate whether x and x equals x at that particular bit, right? So it's like at this bit, is it the case that, pointer? Yes. So I can ask at this bit, is it the case that the values are equal? And I say yes, okay, excellent. I now compute it for x1, once again, x1 and x1, is it equal? Yes. And so I can sort of keep doing this forever. So now my question reduces to, is it the case that this bit stream that I have down here is going to be an infinite sequence of ones? So I've converted my original problem of checking this equality to checking whether a particular bit stream is a sequence of ones, right? So this is sort of the first reduction that I do. Now the next thing that I do is I need some kind of succinct representation of the bitwise AND operation. So in this case, what I do is I represent it as an automata that has a single state. So now, for example, if my inputs are 0 and 1, I know that the output of the bitwise AND is going to be 0. That's given by this transition here, which says that when A is 0 and B is 1, the output is going to be 0. And similarly, I can give you the next bit, where if it's 1 and 1, I produce 1, and so on and so forth, right? So the point is that to compute bitwise AND, you don't actually need to maintain any state at all. You really just need to know the current bits of your inputs. Okay, that makes sense. So now, what's something where you actually need to maintain state? Well, consider, okay. So first, I'm going to specialize the automata for A and B and fuse it with the automata for just the input x to build the automata for x and x. So like there's a fairly simple algorithm that lets you specialize the inputs of one automata with another automata. So this tells me that that when I compute x and x, if the input x is 1, the output is 1. And if the input x is 0, the output is 0. The next thing that I'm going to do is I'm going to build an automata that checks equality. This is going to be a slightly more interesting automata, and we'll walk through it. So first, suppose that both A and B have inputs 1 and 1. Then I know that A equals B at this location. Up to this bit width, I know that they're equal. Now next, suppose I get 0 and 0. I once again know that they're equal, so I produce a 1. Now next, let's suppose I get a 0 and a 1. So they start disagreeing, in which case I produce a 0, and I go to a failure state, because once the bit streams disagree, I need to remember the fact that they've disagreed so far. And so now, even if you start to agree later on, it doesn't matter, right? Because I already have a disagreement at this bit width. So essentially, I need two states. One, so this state says, okay, I'm continuing to be equal. So if the values are equal, I'm going to stay here and produce ones. And then I have a sync failure state that says, oh, once the values become disequal, I really don't care anymore. It's going to stay disequal forever. So this automata succinctly encodes the equality of bit vectors, even when the width is arbitrary, right? Because this is sort of all the state I need to remember. Am I equal so far, or have I become disequal at some point in the past? So now what I can do is I can combine the automata for the bitwise and, the equals, and for the x itself to build the automata for checking the initial thing I wanted in the first place, which is to check if x bitwise and x equals x. So now the interesting thing is, if you look at this automata, you'll see that there are no transitions into the failure state at all. So somehow, like I can ask the question, does this automata always produce ones? And in this case, like for us, you can look at it by visual inspection and you can say, yeah, sure, it always produces ones. If you think a bit, you can also build an algorithm that tells you this, right? You really explore all the transitions and you check if it always produces ones. Exactly, so that's the idea. So that sort of proves our original claim, right? Because this automata precisely encodes the sequence of equalities that we get. And by inspecting this automata, we know that it's always going to be equal. So then, okay, this is not particularly fast. So we implement some much faster algorithm in terms of some model checking thing called k-induction. But fundamentally the idea is really the same. We just use some kind of model checking algorithm to establish this equality, really, to establish the fact that the automata never produces a 0. Right. Maybe just to give you a bit of flavor, it's interesting to see what can be represented by these automata. So for example, we can also represent addition, because intuitively the way to think about it is addition only needs a single carry bit of state at any given point in time. So you start off by trying to add, let's say, 1 and 0. Then you know that the output is 1 and the carry is 0. If you then try to add a 1 and a 1, you go to the state wherein you know that the carry is currently 1 and your output is 0. So now, you have this carry being 1, and you now sort of try to add 1 again. So you once again produce a 0 with a carry, and so on and so forth. So somehow to do addition, you only need 1 bit of carry state. So, right. Then similarly, if you think of equality as a predicate, right? Like equality told us when two things are equal. The automata encoding can also handle things like disequality and unsigned less than, unsigned greater than, signed less than, signed greater than, and all of these things. And also conjunctions of Boolean formulae. Because if you think of P as a predicate, which is 1 when it's true and 0 when it's false, to compute P and Q, right? It's like as long as it's a 1, you stay a 1. And then once you become a 0, you just keep it a 0, essentially. So by a similar reasoning as the equality, you can build automata for Boolean predicates, for conjunction and disjunction and all of these things. So in general, anything bitwise is representable because it needs 0 bits of state. Addition is representable because you can sort of build the add carry circuit and you need 1 bit of state at any bit. Negation is possible because minus x is bitwise not x plus 1. So that's reducible. Multiplication by constants can be reduced to repeated addition. You can build better circuits if you're interested. You can build smaller automata, but this works. You can do Boolean combinations of conditions. You can do left shifts. You can also do right shifts by some clever universal quantification type thing. What you cannot do are things like multiplication, because intuitively when you have a multiplication of two variables, you need like the amount of carry state you need is sort of like as large as the number of bits you've read so far. And this is like an unbounded amount of state which you can't represent in this way. My colleague will be annoyed that I put this slide, but I believe that I can also encode these things. So we're currently having a disagreement as to whether my proof is correct or not. So it's a good thing that we work in a proof assistant where we prove things correct, right? So yeah, I'm yet to actually prove it correct, but I think this works. He thinks it doesn't. We'll see what happens in a week. Yeah, cool. I'm now going to like real quick go over the second algorithm, which is called MBA, for mixed Boolean arithmetic. So first, what is mixed Boolean arithmetic? Well, it's any problem of bit vectors quantified over arbitrary width, wherein you have a stratification of the terms. So the things highlighted in blue, they're all Boolean combinations of bit vectors. And then on the outside in green, you have arithmetic. So you only allow this particular structure of mixing bitwise stuff with arithmetic stuff. And essentially the point is, for this fragment, there are like much faster algorithms. I can give you a formal grammar because we're compilers people, but I think people get what I mean when I say the outer stuff is bitwise and the inner stuff is arithmetic. So, okay, how does this work? So essentially, the idea is, okay, first for bitvec 1, like for length 1, we can just enumerate it by brute forcing, right? Like suppose they're all 0, then this is 0, this is 0, this is 0, this is 0, so it's all equal. Now suppose x is 1 and y is 0. So yeah, exactly. So this becomes a 1, this is a 0, this is a 1, and this is a 0. So it becomes 1 minus 1 and so on. So we just enumerate it for width 1. And now let's try to establish it for width 2. So the interesting thing is you can think of x for width 2 as comprising of 2 bits with x1 and x0. And similarly for y and sort of this is what the expression looks like. But now what you can do is we'll now interpret this as an integer number, which is going to be 2 times x1 plus x0. When you have a bit vector of 2 bits, this is the interpretation in unsigned 2's complement. And similarly, this is going to be the interpretation of y1, y0. And now the clever bit is, if you think of the interpretation of the XOR, it's going to be twice the XOR of the high bit plus the XOR of the low bits. And similarly for bitwise AND, right? It's like the interpretation of the bitwise AND in unsigned 2's complement is going to say twice the bitwise AND of the high bits plus the bitwise AND of the low bits. So, but this now lets me rearrange the formula where I can grab all the stuff in yellow and put it together. But now this is exactly the same as the formula I had established over here for bit vector 1 as being equal to 0. And then I can do the exact same thing for the low bits, where I can regroup all the low bits, and I've already shown that that's already equal to 0. So somehow, because of this mixed Boolean arithmetic structure, what winds up happening is that I can pull out the arithmetic in order to sort of like repeatedly reduce things to the 1-bit case. So that's how this solver works. And yeah, again, we have extensions to this that I think can handle unsigned inequalities, but yeah, not going to get into that. Right, so what can this solve, I guess, like in practice? There's a data set called MBA BLAST, which is by the people who came up with the MBA algorithm. And like roughly, and like we can sort of prove all of them for arbitrary bit width. And in some sense, the specialized MBA solver is like, is 2 orders of magnitude faster than the, than the sort of more generic automata-based solver. But yeah, it's pretty fast. It's like a couple of seconds on most problems, and I think the largest one takes like 15 seconds or something like this, but it's a really large problem. And then we also do something interesting where we grab rewrites from LLVM InstCombine, and we try to prove those automatically. So the one that's like around 7,000, that's where we prove it for the fixed width. And the others are sort of us trying to prove it for arbitrary width. We get around 1,500. And like as you can see, there's a long tail that we don't prove. Roughly speaking, the issues are, for one, we need to be able to generalize the rewrites. Because the rewrites are written specific for 32 or 64-bit, they use constants like 7, right, which is 2 to the 3 minus 1, but that should be generalized to 2 to the w minus 1. Then there are rewrites that use multiple widths, which involve operations like sign, extend, and append. which I claim we can handle. And yeah, anyway, finally, there's some division stuff that we need to handle. But yes, thank you. This was the talk. Questions? Okay, I'm going to, yes.
Can you please go to the microphone so it's recorded? Thank you.
You really have no hope for multiplication?
So I didn't speak about the formal verification, but all of this is proven correct in lean. So the things, so like all of this that I told you, so for example here, right, like I show that if the bitwise AND is equal to 0, then addition equals OR. So this is actually like, this produces a lean proof. And if you screw up and you write something incorrect, then it complains and it tells you that that your theorem isn't true. So essentially, like this like all of the algorithms I mentioned, they're all proven correct in the lean proof assistant. So everything is formally verified. But I didn't have time to go into the actual mechanization of the thing, but it's all mechanized.
My question was about product multiplication.
What was about what?
Multiplication.
Oh, multiplication. Okay, yeah.
No hope at all?
Sorry, yeah. So multiplication we can't handle using the automata theoretic encoding, but I think there are other encodings that play better with the arithmetic structure, which we can use. So yeah, there's this thing called as the two-adic integers, and that has a decision procedure called cylindrical algebraic decomposition, if that means anything. So yeah, I think we can do something with that. Yeah.
So I have a more general question on rewrites.
Yes.
And theorem provers.
Yeah.
Like going beyond bits and zeros and ones.
Sure.
Like, if you want to rewrite the IR, and what are the things we could use? Could we use lean to see if two IRs? I mean, this is going to yesterday's conversation, whether we should just try random rewrites and see if they're all equivalent, or actually there's a formal way of checking rewrites.
Yeah, so like in theory there is, but I think Johannes was right in that, like, it's hard to like define the semantics of MLIR dialects, and it's even harder to prove the rewrites correct. So it's kind of like, I think what would make sense is to at least have a formal semantics, because then tools like Alive can be written, right? Yeah. Like in some sense, the only reason Alive could be written was because, I don't know, like Nuno and John and all these people, they spent ages arguing with the LL, with us really, like trying to figure out what the semantics are. I think someone needs to sacrifice themselves and do the same for the like core.
I was thinking more like, okay, instead of like taking the MLIR per se as is, like suppose I were to craft a dialect and say, okay, in this dialect is going to be really pure, and I define some ops which are pure.
Yeah. So exactly.
And then build and showcase using that, and then see how it can be mapped to things that are broken.
Exactly. So for example, if you look at like the polynomial dialect in the here compiler, like they actually have a pretty like formal specification. So we sort of have a formal semantics of like all of their operations, right? And then I think we've even proven some rewrites about it's called paper examples, but like
that's what we want.
but essentially like we do have like proofs of peephole rewrites here that show that somehow like adding the generator in the ring is equivalent to an identity or whatever. So it's like if you have formal semantics, then this is possible, but like I think developing formal semantics is complicated, and also because MLIR has like pretty complicated abstractions, proving them correct is also going to be complicated.
So you see that for even if we were to craft our own dialect with some very example ops, even then it would be a problem.
Well, no, it would not be a problem. It's like you would need somebody to either come up with an algorithm or like a reduction to an SMT problem, like Alive does, or you'd need somebody who knows how to use a proof assistant to prove these things correct, right? Or, okay, there's also the third option that AI gets good enough that it just automatically does it, but, who knows? So I think those are the three options, really.
Yeah. Okay, thanks.
Yeah, you're welcome.
Thanks. That was a really great talk.
Cool.
I was wondering, do you handle undefined values or poison in any way, or is that...
Yeah, so... Right. Okay. So like roughly speaking, not directly in this encoding, but it's kind of like, but in some sense we can do what alive does. So what alive does is, so here's what alive does. So it finds the set of inputs under which the program is undefined, and it shows that the target refines the source, which is a set of constraints that we can prove using the automata technique. And then it shows that, when the program is defined, then the target and source have the same semantics, which are also expressible in the fragment that our automata can handle, right? So it's kind of like, as long as you use operations that are within the fragment the automata can handle, then the UB conditions are also within the fragment that the automata can express, essentially. So yes, like we haven't done it. It's theoretically easy because, like the alive people did all the hard work of figuring out the conditions. We need to write the pre-processing. But that's sort of how it would go. Yeah.
Okay. Thank you.
You're welcome.
Thank you very much, Siddharth. Now we will have a break for lunch. Thank you very much.
Thanks.